afternoon, everyone, and welcome to today's ZEBx Decarb Lunch. My name is Natalie Douglas, and I'm the Program Manager for ZEBx at the Zero Emissions Innovation Center, otherwise known as ZEEC. Today, we have speakers from Stantec and HCMA to talk about prefab mass timber innovation at the Royal Roads University John Horgan campus. They'll chat through how they placed operational and embodied emission reduction strategies at the core of this project design and design pivots that they had to make, a deep dive on the facade, and some overarching takeaways. So it is a project that, although unique in some components, it definitely has elements that can be applied to projects beyond just an institutional building with a heck of a lot of sustainability buy-in. And there are also going to be a couple other folks from the project team that are attending this webinar, so they'll be in the chat able to answer questions. We really encourage folks to engage there in the chat, ask questions, add relevant resources or events, provide commentary. We want this to be a discussion. I'll also draw commentary from the chat to help guide the panel discussion at the end of the webinar. Today, I'm joining you from the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh nations. They and many other nations across BC have really taken lead on placing environmental well-being and energy and carbon performance at the core of their projects. So just something to keep in mind as we're moving through this work. I'd also like to thank the City of Vancouver and BC Hydro for their financial support. Their support enables us to offer these continuing education accredited webinars for free. My colleague Victoria is going to drop some details about continuing education credits and receiving those, and she'll throw those in the chat right now. Victoria is also going to launch our first poll just to give us a sense of who's actually in the room. And it would be really appreciated if you answered that. It gives us information to allow us to adapt the offerings that we have. And before we dive into the presentation, I also want to thank BCIT for acting as a co-host for today's webinar. The BCIT Building Lab legend himself, Alex Hébert, who I'm sure many of you folks already know, is going to help facilitate the Q&A portion at the end of the webinar. So as you'll learn in part of the presentation, BCIT is really crucial to elevating some of the key learnings from this project. And I'll just leave it there on that cryptic note. I'll pass things over to this excellent presenting team, Franz Greenwood and Elise Wooston from HCMA and Simon Wong from Stantec. So I will pass things over first to Franz, who's going to kick us off. Over to you.
All right, excellent. Thank you. And good morning, everybody. I was the project architect for the John Horgan campus. So I'll just quickly go through the agenda for today. I'm just going to walk you through some short project context items, then pass it off to Elise for a walkthrough of the carbon story that we were really telling with this building. Simon will give you sort of a play-by-play on the facade design, and we'll wrap up with some next steps, essentially lessons learned. So the project context, the why and the where, essentially, for this project. So I'm sure some of you have heard of Langford. It's a municipality just to the west of Victoria. In the 2021 census, Langford came up as being the third fastest growing municipality in the country. And despite some of these amazing accolades and achievements that this sort of municipalities could have gone through in the last several years, its transition of students from high school to post-secondary was lingering far behind even the provincial average. So about 17% of high school graduates from Langford and the sort of wider West Shore were actually transitioning to university, which is half the provincial average. And this is despite them enjoying a 20-year high of high school graduation. So it wasn't for lack of options on offer. As you can see, there's a number of post-secondary institutions in the region. And so there was this identified disconnect between the school district 62 and all these opportunities. And so as a collection of institutions, they got together to seek out a solution to this matter. Next slide. So So one of the issues at hand was identified as a geographical one. A lot of these institutions are actually fairly far to the east. Langford and the Sioux School District is fairly far to the west. And actually, the commute itself was identified through survey as being one of the main inhibitors to a lot of students transitioning to these institutions. So, of course, rather than expecting the students to simply come east, they gathered together to decide to bring the campus to the West Shore itself into the heart of Langford. Next slide. And so this is our location right in downtown Langford, right at the intersection of Goldstream Avenue. This is essentially the main street in Langford and the busy intersection with Pete Road. Quite a large swath of land was purchased by Rural Roads, and the first building on this new campus enjoys this point of visibility, very accessible, transit ready and bikeable right at that corner of the site. Next slide. And just zooming in a little, this just gives you a sense of the layout of the building, very simple sort of two-wing arrangement along both streets. On the one side, a very sort of socially focused program, one that connects students and the community itself, whereas the other wing predominantly focuses on sort of education programming. And importantly, on the ground floor, in this case, the school district itself had its own space, so allowing students that were considering transitioning to post-secondary to come to the building, find some spaces very easily, and have the opportunity to intermingle with the post-secondary cohort as well. And so the building is complete. It opened its doors to students for the 2025-2026 school year, and hopefully many years to come. Next slide.
Thank you,
Pass
Franz.
it off to Elise here.
Yeah, thank you. Next slide, please, Simon. Thank you. So the project started with the submission of a business case to the ministry to secure funding. And as part of the application, the ministry requires you to demonstrate how the project aligns with their priorities, such as Clean BC and the Woods First initiative. And so to ensure success, the project team committed to a pretty ambitious sustainability agenda, which included designing an all-electric energy efficient building, using a mass timber structure, and pursuing LEED v4 Gold and the Zero Carbon Building Standard Design Certification V2. So really, this was our starting point, right? Once the business case was approved, this set the trajectory for the project. There was no more questioning about those things. We're just, going forward with a pretty intensive, pretty stringent requirements in regards to sustainability. Slide, please. So about halfway through the design phase, the city of Langford became the first municipality to mandate low carbon concrete for most projects by adopting the carbon mineralization policy. So that policy requires the use of carbon dioxide mineralization technologies such as carbon cure. And I think the railroad project was actually one of the first projects to fall under that policy. That policy was actually replaced about a year after it was adopted for a more performance-based approach. That approach was very much prescriptive, and so the policy was revised in 2023. However, this was applicable to our project. And so next, please. So this is really the context we were working with, right? With very ambitious carbon-focused targets, and the carbon discussion was very much at the center, at the core of the design process. The focus was on both the operational carbon, so that's the carbon associated with the building's operation, as well as the embodied carbon, which is the carbon associated with the construction materials. So I want to run through some of the design strategies that were implemented on the project to reduce the operational carbon and the embodied carbon for the project. So some of the first strategies here that you see are related to passive strategy, So nothing extremely, special here, but we have designed the building with triple glazing, decent amount of insulation, reasonable, window to wall ratio, and demand control ventilation. Next slide. On the mechanical system side, all systems were electrified and selected for their efficiency. So the main heating and cooling plant consists of 2 air source heat pump with some backup electric backup boilers and dry cooler for the backup. On the domestic hot water side, we are relying as well on the air source heat pump for preheating, and the top-up is provided with an electric domestic hot water tank. And then finally, on the ventilation, we are also relying on ventilation with heat recovery. Next slide. Thank you. So we do have a fairly large array of PV, of photovoltaics on the roof, with about 118 PV panels, which cover 8% of the total energy use of the building. So another strategy to reduce the operational carbon. We're now switching to design strategies that were implemented to reduce the embodied carbon side. And that includes the use of the mass timber structure, right? That was a business case commitment. So the structure of the building was designed with CLT floors, supported by glulam columns and beams. We do have a few concrete elements, which were the shear walls and the elevator and stair cores. Next slide. So we did implement some low carbon concrete mixes. So to comply with the Langford policy, we have used the carbon cure mixes, which pretty much forced us to sole source the concrete to Butler at a time. Next slide. And so we actually pushed Butler quite hard on during the procurement to make sure we received detailed information about the various mixes. Next. And with that information, so we've received a very detailed information about, where each mix was sourced, the volume of concrete for each mix, the global warming potential for each mix, and the reductions in global warming potential compared to average mixes in BC. And so we were able to confirm that the project overall for the concrete scope achieved a 33% reduction in embodied carbon compared to BC average mixes with an average SCM content. So that's the supplementary cementitious material of 40% overall as well. Next slide. And finally, on the embodied carbon perspective, the project was also designed with the prefabricated mass timber façade. So the façade is made of LSL panels with glulam posts. Simon will dive into the details in a few minutes, so I won't spend much time here. Next slide. Okay, so some energy and carbon numbers here to give you a sense of where we landed in terms of the performance with all these strategies implemented. Next. Thank you. So just to give you a sense of reference, you can compare those results with some benchmark numbers I've put on the slide to the right, which are coming from the building benchmark BC data for the total energy use and operational carbon, and the CLF benchmark explorer for the embodied carbon intensity. So TD total, oh, sorry, go back one slide, thank you. The thermal energy demand intensity is about 21.7, so quite low there. Total energy use of 73 kilowatt hour per square meter per year compared to the average for this typology in BC based on 2024 calendar year of 238, so quite a reduction there as well. GAGI is the greenhouse gas emissions intensity, again, all electric buildings, so we are achieving a very low number. And finally, on the embodied carbon side, we are at 363 compared to the 479 for, again, the average in North America for that typology. And sorry, I just want also to clarify the embodied carbon piece is focused on the structure and the enclosure of the building. which aligns with what the zero carbon building standards and LEED were requiring. Sorry. Next slide. So diving in a little more on the embodied carbon results. So you can see the bar on the right represents the building as constructed. And the bar on the left represents a functionally equivalent baseline with a concrete structure, conventional steel stud assembly for the exterior walls, and average concrete mixes. And the bars in the middle represents the various savings achieved in embodied carbon with the various strategies implemented. So from the concrete structure, by changing the concrete structure to a mass timber structure, we've achieved a pretty significant reduction of about 33%. We've achieved an extra 1% of embodied carbon savings through the use of the mass timber envelope façade system. Achieved further, 5% with the low carbon concrete. The number is fairly low here because the amount of concrete in the mass timber option is fairly limited. So the benefit of the low carbon concrete was somewhat small compared to, the switch for the structural system, for example. And then the last strategy that was implemented was the use of sole sourcing of the XPS insulation product to the Suprema product, and we've achieved another a few decimal of percentage there to switch to the Suprema product. Next slide. And so here is the overall carbon balance for the building, including the operational carbon and the embodied carbon over 60 years. And you can see we've done, a lot of efficiencies on the operational side of things. So the embodied carbon represents here still the vast majority of the emissions of the building in this case. Next slide, and I'll pass it along to Simon.
Awesome. Thanks, Elise. Yeah, so the facade design, and I guess before we get into the facade, kind of just want to highlight, why did we do mass timber? Why do we do mass timber in general? And if you haven't done a mass timber project yourself, usually what you hear from the industry and what they sell you on is, hey, it's low carbon. You're gonna have versus concrete. You're gonna have some better control of your schedule because it's prefab. You get a nice, precise manufacturing of the building components, and it's lovely to look at. It's very biophilic. People like wood. It's nice in a building. However, what they don't often tell you is that these benefits aren't inherent to your material choice. So that's why we kind of wanted to take a different look and look at, hey, what's the net carbon? How can we manage and improve logistics delays? How do we manage, that precision comes at a cost for manufacturing. You need to develop the design a little bit further than you would in a traditional kind of project. And then how are we making things more challenging on the means and methods level on the contractor side based on how that designs come together? And so the solutions really just have to be very balanced and deployable, not really isolated in our own silos of, hey, I'm an architectural consultant or I'm an engineering consultant, and it's just about looking at a holistic kind of systems approach across the industry. So the other point that's really crucial to think about is what's our carbon balance on a lot of these high performance projects. In the past couple of years, we've all been pushing really hard into actual just performance of our building assemblies, right? So that's adding more insulation, that's finding ways to get thermal breaks into it. We have innovative solutions for most projects that are done and really targeting the zero emissions. However, now we're finding, the graph that Elise just showed with the amount of embodied carbon is that we have to balance this push towards performance with thinking about embodied carbon of like, okay, how much material are we putting in and is that all necessary? Can we find lower embodied carbon materials? Where can we reduce waste? And what kind of emissions are we actually accounting for in our overall calculus? So one of the things about mass timber too is that there is this kind of a big risk item that isn't necessarily talked about as directly that plays into every facet, whether it's cost, whether it's speed, whether it's even carbon. It's not just about the kind of one metric you're looking at. You have to look at the overall, risk profile of the building and the system. So whether the system selected is good for airtightness detailing, whether you're introducing additional deflection gaps between materials, how poor of a thermal bridge that interfloor transmittance might be, how long you're actually exposing the primary structure to the weather versus having it being closed in, and whether you have a continuous prefab plane. And the one piece that's really critical is, is there a kind of coupling of your envelope and your secondary structure with your primary structure? So, we're talking 60 years down the road. During that time, is any kind of small failure within that building envelope or kind of a maintenance oversight going to result in a bigger problem that actually affects the primary structure? So now your envelope, if that's integrated into your structure, then those two problems will come hand in hand. So you want to kind of get away from that. And I think one of the things we found really for all mass timber buildings is kind of bypassing the wall outside of your primary structure makes a lot of sense for mass timber buildings. So when we find things that make sense, then those are the ones we want to carry forward. And if they can kind of address multiple items, then the value really starts to show on the value side of the cost value equation. So the project did start out with kind of a more traditional mass timber wall look. So that would be, CLT or GLT system. And then we kind of did land on a composite level where actually the amount of wood was allowed to be reduced. This is very similar to kind of other technologies in the wood industry. Traditionally we've gone from a dimensional lumber 2x8, 2x10 joist to now the very standard wood eye joists that are commonplace in all kind of wood construction. So for this project, we just wanted to share with you the journey of this whole project and how it all came around, and really just share, here were some of the challenges. We got some great lessons learned and successes from it, but it wasn't all super smooth the whole way along, right? So the design was kind of finished up in 2022. Durwest Construction Management was construction manager for the project, and they kind of began the site work there at the late 2022, moving on to the concrete and the steel in the middle of 2023. Around this time, because mass timber, you have to engage early, you have to get things integrated. So the team was very good at doing that. However, the company that they went with, Structurlam at the time, unfortunately became insolvent. So the team was able to turn around fairly quickly on the structural mass timber portion and actually get Kalashnikov on board to kind of fabricate and still hit the timber structural install. However, at the time, we were still missing this piece of the facade, which was being worked out with Structurlam, but hadn't quite gotten over the line. And we were finding some difficulties. Kalashnikov at the time wasn't offering a facade system. So we were trying to hit this date of, okay, we got the structure going. It has kind of an end date. We're going to need a facade system and solution by this time. So that's where we came along, Stantec, to do a design for manufacturing assembly, which just means that you're kind of partnering more with suppliers, with kind of manufacturers to improve the design and make it feasible, right? So Weyerhaeuser was one of the partners that came along. And if you don't know about design for manufacturing, you're essentially trying to make the manufacture easier. So how do we make these parts easier? And also assembly, which how do these then parts that you've made up go together easier? And just trying to minimize and make things more efficient. And the other targets, again, focuses was on carbon, was on performance, and also about cost and the net cost, which kind of drove a lot of the decisions in this process. We looked at the thermal bridging and effective performance. So this is a whole nother topic we could dive deep into, but actually we achieved an effective R21.9, essentially 22, considering that 33% window wall ratio and all the kind of detailing that comes within a project, so that it's not just, okay, you have a great thermally performing clear wall, but it's looking at, okay, overall in this building, where are we losing out on our thermal efficiency? What's our actual effective wall, and how can we get that working really well through the design of that clear wall as well? So ended up 68 unique panels, 163 total panels over the project, and I think it was divided up in 5 phases. And just wanted to share quickly about how the actual panel goes together. So it's a combination of either PSL or glulam posts. Those take care of the dead load and the wind load of the panel, also provide a back channel for the window. And then we have these LSL panels, which is essentially a rim board kind of material that ties it all together, provides a diaphragm, infills the wall as well. So all your clips can actually be assembled onto that. And then the window frames go into there, your typical membrane clips. Kind of anything can happen from this point outwards, but that kind of provides the main structure of the wall panel, and it can be kind of reconfigured in different ways. So the piece with the efficient detailing is that post, that glulam post that we used, ended up being the back channel for the window. So if you imagine your typical curtain wall profile, you have kind of your veneer system of where the glass unit gets sandwiched between, and then you typically have a aluminum back section, possibly with a steel integrated, to actually provide the rigidity and structure for it. In this project, we went with glulam, and that was actually formed a part of the panel, so the window and the panel are all kind of integrated into this one element. Further to that, with the reason the glulam was used, and kind of PSL and LSL can also be used, but in this case, this was also became the kind of window jamb finish. So really nice windows. If you go to the project at any time and take a look at those windows, really nice kind of wood trimmed out jambs. And the kind of precision milling, we went to the extremes of going down to the factory, figuring out, okay, this is the profile we need to create out of these timbers. How can we actually cut it better? So then diving deep into the actual fabrication and the cutting processes of these actual machines, you can find actually if you sequence the different cuts in a certain manner, well, you can actually get huge improvements to the cut time per piece. So this is really when you get into the nitty gritty of, okay, this machine is designed to cut in a 6-axis format. They have different bits that they can interchange between. How can you make the most efficient use of the bits, and where can you kind of put notches or maybe even omit or delete notches so that you can actually have improvements there for future manufacturing. And the other piece too is like we kind of came across this way of making it very easy to manufacture, right? This is actually all set up on the side of a mainline modular manufacturer. It didn't disrupt their regular process. It was quite easy to actually put together. And this concept of micro contracting can also come in. So this manufacturer did have the machine, the 6-axis CNC, to actually be able to cut the posts. However, in a future state, you can actually have this outsourced, and I think this is, I'll talk about the BCIT project later on, but you can actually have different parts kind of created at different specialty areas and kind of bring it all together to be assembled. And just by using the, so the other slide we showed, okay, going from CLT to structural composite, we can reduce the amount of wood fiber in the panel overall, so about 32%. But also the switch to structural composite means that you actually get to use more of a given tree or a piece of lumber from the forest, right? CLT being manufactured from dimensional lumber. As you go through a mill, you can only get so much dimensional lumber out of it, whereas your structural composite kind of takes those additional pieces, the waste, and kind of puts them all back together. So continuing on down our path, we did the DFMA process. We kind of came up with this panel, issued a fabrication set of drawings, and got to our fabricators, which were ATCO. The field envelope installers, Top Line Roofing and Rutland Glass, who did the glass, also kind of came into the factory setting to install portion of the panel there. And we were actually able to hit that facade panel install date, not without some pressure to get all of that kind of turned around in 7 months. if done ahead of this, I'm sure we could have found additional benefits on future projects rather than kind of a knee-jerk reaction and trying to problem solve when a major supplier goes under. So because of these restrictions on timing and kind of how trade procurement was already happening, the only part of the wall was actually prefabricated on offsite, and the rest was still installed on site. So just a couple shots of how that looked. Panels were installed. The membrane was on and complete. The glass was done. However, the window channel, the first piece of that frame, was already in. And this is how it would look from the inside. We still did come up with some issues, you know, between communication onto the field, because mass timber is really good at being accurate. However, there's still some field kind of tolerances that come up. So I think in that second photo there, you see the steel beam actually protrudes further out than the CLT, which kind of made an issue because now this beam is interacting with one of those posts. And then there's some shimming and washers that go in there. So partial panel didn't affect actually the kind of critical path of the project, which is really good. Because the finishing still took its time, which is something we want to address on future projects. However, it did take quite a long time to actually finish up that envelope. So you'll see here, I'll click it quickly, but if you blink, you might miss it. The envelope panels go on really quickly, and then you kind of have the rest of the project duration as you wait to actually get that panel finished. Did not really kick off the you know, the interior finishing and the overall project finishing, but you have this kind of gray zone of like, well, there's a lot of efficiency loss there that we can't necessarily quantify, and that subtrade who did the work, they had to do probably a lot more of it. They probably would have made more money and been more successful and want to do this again if they had taken all that work offsite. So kind of some things to look through in future projects and planning of. And the calculus of how is this worth it? Where does the value come from? So this is just a shot of the interior with the drywall done. And then following that, we also had the panels taken down to Intertech to do the seismic and drift testing. We actually provided the fire stop engineering judgment for the panel as well. So it was quite successful because we found a way that we could hit our thermal performance targets, make the airtightness really simple in a low carbon way by using this structural composites. Turned out to be really deployable. This building wall type works for like all different types of buildings, commercial, institutional here, actually works well for residential as well. And we're looking at industrial now. Can be adapted to various types. So this is a double in the atrium area. This is a double height wall. So that's just two panels. You see that cross beam that actually supports the panels there. And it actually became quite cost effective overall. And Elise will dive a bit more into the specific comparison on the embodied carbon of the panel.
Thanks, Simon. So yeah, we did do a little bit of a dive deep into the embodied carbon of the panel system. And so the study was done on one of the panel, the one that you see on the screen there, 6.1 meter per 4 meter. We've only looked at the embodied carbon emissions scope A1 to A3. So it's, you know, often also referred to as cradle to gate. So it's the fabrication stage of the products. We have excluded the glass, any fasteners, but we have included all of the steel connectors that were needed to put those panels together. Next slide. So we've compared the system that was constructed on the right to like a conventional wall assembly, which we use on a lot of our projects, which is an uninsulated steel stud wall, interior drywall, exterior drywall, and exterior semi-rigid mineral wool insulation with clips and cladding. So the comparison here, you can see the two different assemblies compared. Similar, very similar R value, clear fields for both assemblies. So on the left, you see the steel stud assembly with the exterior insulation, 6 inches of exterior insulation. On the right, you have the assembly as built which has 2-inch of rigid mineral wool on the outside, the LSL panel, which is 44 millimeter thick, another 4-inch of rigid mineral wool insulation on the inside, and then furring with steel stud and drywall on the inside. Next slide. So the window system is a bit different in both options there, as Simon mentioned earlier. So in the as constructed approach, we see it on the right, you have only the curtain wall mullion is only really the front part, because we are relying on the glulam post of the panel as the back section for the curtain wall support. As opposed to the left side, where we have a traditional curtain wall systems, so more aluminum in that wall assembly for the back section. Next slide. So these are the results, the comparison between the two models or the two wall assemblies. So you can see there the greenish color, the various greenish color shows all the metal. So on the left side, you can see most of the embodied carbon from metal elements, whether it's the cladding, the Z-girth, the steel stud, or the curtain wall back section. On the right side, that portion is definitely strongly reduced. Interestingly, the insulation choice in the mass timber option hurted us a little bit on the embodied carbon side, because the rigid mineral wool insulation is almost double the embodied carbon of the semi-rigid stuff. So definitely an increase in embodied carbon there on the insulation side, but overall, we're still achieving about a 14% savings in embodied carbon for the A1283 scope. Just a few clarifications there. So this is comparing two systems that are that have an equivalent clear field value. But as Simon mentioned, we know that the mass timber approach allowed us to improve some of the detailing around the building, such as the parapet detail or the slab edge detail. And so, potentially the mass timber option may have allowed us to reduce the amount of insulation overall to hit the same effective R value across the building. So we haven't accounted for that, of course, in this study. We haven't accounted for the fact that the mass timber wall is substantially thinner than the steel stud assembly, meaning it could result, if you're considering as an equivalent net flow area, you would potentially see some savings in materials due to thinner walls. And we haven't accounted for any, benefit of the prefabrication system as well, such as reduced waste. Next slide. And I'll pass it along to Simon again.
Yeah. So next steps, the wall was then, partnership with Suprema again. They took it, they got it tested under the CAN ULC S134, which is their flame spread rating. So now we have a timber-based wall that actually passes an S134, enabling it to be used actually kind of in high-rise construction now, which is really great. And then the next iteration of this project, we took the same wall, made a couple minor improvements here and there, and detailed it out, and actually installed a full-size mock-up at BCIT's High Performance Building Lab as a part of a tall wood mass timber mock-up. So that this is a kind of concept of, hey, what if we took a section out of a future timber tower and put it on display, right, for teaching? So it actually includes a balcony connection detail. It has the protected assembly on the outside, and actually has a prefabricated interior that would be suitable to be used. And so it's just really highlighting and showing off this element, so that we can, once we've learned something, we want to be able to share it with others and kind of push this industry forward, because all of this design is actually pretty much open source. It's not linked to any supplier. It's not kind of locked into a certain brand. It's like you can go buy these components and assemble this wall together and be able to actually use it in buildings, and hopefully that kind of helps with the adoption into the industry. Alex, did you want to say anything about the lab while we're on this slide?
Yeah, I guess maybe just sharing an invitation to everyone who wants to see the mock-up. It's fully complete now. We have an open door policy, so you can actually come anytime. The doors are unlocked 9 a.m. to 8 p.m. If you want a guide, tell me in advance and I'll get you someone to walk the mock-up with you. But it's really, really cool now that we have the full assembly, and we're hoping everyone can learn from it.
Yeah, and there's a lot of little. I think they've added like all these educational notes and things, so you can. It is almost like a self-guided tour now.
Yeah, that's a good point. It's actually quite self-guided already.
Unless you want to open the big doors, that's a specialty one. But yeah. So then, yeah, back to the kind of talk about insulation products.
Thanks, Simon. So yeah, just another lesson learned is, by switching. So this project used, as I mentioned earlier, the rigid mineral wool insulation product. They've actually used on site both the rock wool product and the power wool product. But what was interesting and what we've learned is those two products are really made for exterior applications. But in our case, we're using those products on the inside of the building. This is a lead project. We couldn't find those products weren't tested for VOC emissions. So, something to consider, when you start to use exterior materials in the inside of your building, you might not have the same type of documentations and testing. Not to say that they're not compliant, there's just no testing available for those products because they are really not meant for an interior application. And next slide. And just wanted to come back to that the embodied carbon comparison between the mass timber wall to the steel stud wall. Something that I've glanced over purposely earlier is the cladding piece. We've made some great savings from switching from steel stud to mass timber, but you can also see that the cladding option there, the cladding selection represents almost half of the embodied carbon of the wall. The cladding that was selected on this project was an aluminum panel, a thick aluminum panel. Friends can elaborate on why that product was selected. But so it is certainly a high embodied carbon product. And something to consider, for kind of next project is I think the earlier in earlier design, we were leaning towards an SEM panel, a composite metal panel. But due to the combustibility challenges, we switched to the aluminum product. So I did quickly do a quick check whether, what happens if the product was selecting a steel cladding, a corrugated steel cladding, concealed exposed fasteners, and there are definitely more substantial savings available if you start addressing the cladding materials as well. So you can see there, we've reached 39% savings if we switch the cladding to a steel cladding, a corrugated cladding. And then finally, you have seen that our focus has been really on the operational carbon and the embodied carbon. Retroactively, we've looked at the refrigerant leakage. The project has 2 heat pumps and a small condensing unit, both using R14A. And you can see that the emissions related to refrigerant leakage over 60 years are pretty intense, almost as bad as, almost equal to the embodied carbon emissions. Of course, if we were to build that project today, the regulation context has changed quite a bit since that project was designed, and we are likely to see, other types of refrigerant being used in those air source heat pump. But that was certainly a learning for us. Next slide, please, Simon. And yes, it's we have about 42% of the emissions related to refrigerant leakage. Next slide.
Yeah, so some of our key takeaways are really just to take a systematic approach to the design overall. You're trying to balance all of these different things, from the performance to the carbon to the cost. And so there's real world constraints. There's ways you can get more value. There's, design constraints. We just talked about the cladding. So all of these constraints, it's just trying to iterate and do better than you would have, and a little bit better. Someone said, okay, it may be 1% difference changing to this to a different prefab facade system with mass timber, but kind of what's the bigger picture? What's overall, is that kind of driving other value benefits to it? And also, hopefully in other projects that people complete, as you have things you learn, hopefully you can share about them, both the successes of a project and the challenges, so that the rest of the industry can move forward and learn. So we're hopefully trying to do that through these webinars and also through BCIT's Learning Lab.
And last takeaway, be aware of blind spots, right? We've been, our focus had been on, embodied carbon and operational carbon. We've talked about the refrigerant piece. We've talked about the cladding selection and the insulation selection. Really, we need to be aware of, what are we not considering right now? We could have also looked at, the MEP systems, the embodied carbon of the MEP systems, or the embodied carbon of the interior partitions and interior finishes, right? So we are well aware of, how limited our view of the project, might be in certain cases. But so we're obviously trying to, make improvements as we go, and at least being aware really helps to change your perspective on the work that you're trying to do on a project.
Yeah. So that comes to the end of our formal presentation there. Feel free to reach out if you have any other questions. And I think Alex is opening the floor here for some questions.
Yeah, I wonder if you, Simon, could go back to the one of the early slides where we saw the reductions going to a mass timber structure that was quite good, and then the quite limited reductions in embodied carbon from the switch to a mass timber envelope. And so I guess the question is either for Elise, Simon, or both. If we were doing a bit better with biogenic carbon and considering time of emissions, would that reduction from going from maybe a more standard facade to a mass timber facade show greater difference here?
The biogenic carbon, absolutely. So we are not accounting for biogenic carbon in those studies, as in accordance with what LEED is asking and what ZCB is asking as well. And sorry, your other question, Alex, was
I suppose that there's also in an LCA the concept of considering what happens at the end of the life of that wood structure that will potentially be burned or decay again. But really, in the short term, you're avoiding emissions of producing metals and other product. And I'm asking this question a little bit as a lay person because I'm not an embodied carbon person. But in reality, are we not having a greater impact on reducing emissions and impact on climate change than what this graph shows?
So the scope here is structure and enclosure, right? So that's the first thing. So in a building, the embodied carbon of a structure is it's probably around 75 to 80% in the buildings that I've worked on in general. So as soon as you make savings on the structure, you see big savings overall. The enclosure is already a small part of your embodied carbon. It's around 25%, 25%. So even if you make big savings, the savings overall are going to be fairly reduced. So it's just math, right? So yes, for sure, if you were accounting for the biogenic carbon, the picture would be quite different on the facade, and you will see higher reduction. I'd say, again, the cladding and the insulation choice would have achieved higher savings. In terms of and this study is, and sorry, I didn't share that on the screen, but this graph was for A1 to C4 scope. So that's cradle to grave, including end of life stage of the products, right? So we are accounting for the difference in, recycling of steel versus, I'm not sure what the software that we are using is assuming for wood, probably composting in the study.
Awesome. Super clear. Thank you. Nathalie, over to you.
That's great. Thanks, Alex. Yeah, there was a lot of conversation in the chat, so definitely a project that a lot of people are interested in. Some more specific design questions. I'm just going to go through a couple of them. One of them being, is there an opportunity to have the exterior finishes completed in the factory similar to module projects with just tie-ins on site? Do the manufacturers have this capability at the moment? Just reflecting on kind of that repeatability aspect of this system that you guys developed.
Yes. So the simple answer is yes. This project, the trades were engaged to do a on-site kind of finishing, and didn't really necessarily want to break that up. If it was earlier in the plan to be kind of completely fabricated off-site, that could have been done with the kind of stitch up tie-in. And then it kind of goes back into the architectural question of, if you want the building not to look like it's modular or prefab, perhaps you do want to actually finish a lot of that cladding on site to be able to hide all these join lines too. So there's options, and it's kind of flexible in terms of how much you complete. The more you do off-site, the kind of more kind of perpetual benefit you get, or kind of snowballing effect you get. And that's why at the BCIT lab, we also showcase the interior prefab, because we found, okay, we can shrink the exterior schedule, we can shrink the structural schedule. What's kind of next on the target list is like, oh, the interiors. If we can kind of reduce the time there, then now we're looking at real gains in the overall project duration.
Another question on design, probably for Simon. Would the envelope not have benefited from having insulation between the interior steel studs?
I don't think it was necessary at that time. So that goes back to their carbon balance of like, how much are you putting in between? If you add more insulation, this project didn't really need to kind of perform even better. It was already quite good. And that was like the minimum amount of insulation needed. An effective R21 wall is actually quite good. I think most buildings are probably even only targeting an R15 under step code. So yeah, you can, but it's, what's the value of that? Is it worth pushing that? If you are trying to hit a passive house target, perhaps that does make sense. And then it might go back to the question, now we're more informed, okay, is it better to add that in the interior steel stud? Or is it actually better to kind of increase the thickness of the exterior insulation? Thinking about, hey, that would give better performance because it's on the exterior and not thermally broken up by the studs, versus that's a higher embodied carbonate type of insulation. So a couple things to weigh and pick between.
Yeah, and remember that cavity was made for conduits and junction box and everything, right? So we would have like that insulation would have been the amount of thermal benefit that you get from that insulation between the sub is fairly limited, because it's broken down by each slab, the slab edge, the studs, and all of the conduits and penetrations that you have in that furring wall.
It's also the cost of the trades too, because if you think about, okay, a trade is already putting exterior insulation on, maybe it's 2-inch, and now they're going to buy the 3-inch version and install that. The only difference is the cost of the insulation now. If you're adding additional insulation to a stud, now the stud tray has to finish before it actually gets insulated. So you're actually delaying and adding additional work. So that might not make as much sense kind of overall. And that's kind of what we're talking about when we're thinking about the system.
Yeah, makes sense. I think this relates to a bunch of different questions that were asked in the chat about performance and airtightness. Alex, do you want to jump in and ask some of those questions?
Yeah, so quite a few good questions, Simon and Elise, about airtightness. So at a high level, can you explain to us what was the main air barrier strategy for those panels, and definitely talk about the connection between the panels once they are assembled on site? And I guess a question linked to all of this would be, how airtight was the building at the end? Do you know the result of the airtightness test?
I have it written down somewhere. At least I don't have the actual number.
So there was no whole building airtightness test on this project. They scoot right before step code became mandatory. But there was a compartment test, right, Simon?
Yes.
Yeah.
So
in mid-construction.
We did quite well. I mean, the compartment test doesn't actually give you a number, and that's not the point of it. It's supposed to identify where there's issues and leaks, and we didn't find any on the panel itself. It's kind of the membrane, the air barrier membrane goes directly on the panel, and so it makes it a nice flat continuous surface to be tied in with the adjacent panels. And I think part of the strategy that makes that work, which is, or part of the improvement from, say, an infill steel stud is when you actually infill steel stud between CLT floors, you have to allow enough kind of deflection channel at the top of each wall. And that becomes the difficult part to actually seal in your air barrier and deal with. And sometimes it actually turns out really ugly on the inside because you need to provide a bulkhead to show, to kind of conceal and hide that deflection channel. It can be like 2-inch deflection channel. So it was kind of like looking at, if we were kind of in place building a steel stud wall, then you're just challenged with all these different details and intersections that you have to put membrane around. And the thing with mass timber panel, or just kind of envelope panels in general, is most of that clear field of each panel is quite airtight because it's a lot easier to make it airtight.
And can you speak quickly at the BCIT site? You also had a bit of a gasket approach in between the panels. Was that something added at BCIT, or did you have that at the Langford project as well?
The Langford project, we were testing it, and we actually tested it with a very simple rod and caulk solution between the panels. And that worked well for the kind of building size and conditions it was dealing with. And at BCIT, we're kind of looking into, and eventually we actually omitted it from the project because different project parameters will require kind of different sealant joints between the panels. So we wanted to leave that a bit open-ended. But yeah, the Royal Rose one was actually done with a very simple rod and caulk that provided really good air sealing and not enough movement to make that matter. But yeah, other products, there's like expandable gasket seals that could be used.
Thank you. Natalie, I see you launched the polls. I'll give you the mic back.
Thanks. I'm going to shove as many questions as possible. So I'm going to ask one more question and then wrap it all up. There were probably 4 or 5 questions regarding FCM specifically, and that potentially can be answered a little bit more quickly. I don't know if this is, Elise, a question for you. Was there added cost to that 40% FCM mix? And then any reflection on that managing schedule piece? Obviously, curing times change a little bit. So any thoughts on that?
Yeah, on the cost, I don't think I'm able to provide much information. That would be a question for the construction manager. Franz, do you have any recollection of whether those mixes had impact on the schedule? But I would say it's a mass timber building, right? So the concrete is mostly in the footings. And so often the footings do not have much impact. There is no shoring, right? So the impact on schedule is typically limited for those elements of concrete, right? And the only other small amount of concretes were, those cores and shear walls. So Franz, I don't know if you recall any impact on schedule?
On schedule, well, it was a phase tender as well, so we did try to push out the concrete component ASAP prior to the rest. So as far as cost goes, yeah, not aware of what impact that had.
Sounds good. Well, that could have been a whole nother webinar. I know that we were trying to fit in a lot into this webinar, and I really appreciate all of your guys' frankness and willingness to share about this awesome project. We could truly write a case study probably about many different elements of this project. And I know there were many questions that were posed in the chat that were not answered. Many of them answered by other folks in the community, so I really appreciate that. Thank you again for sharing. I'm going to throw 2 events that the ZEBx and fellow building decarbonization teams at ZEEK are putting on. There's one in Victoria, modernizing or powering modern buildings. That is a really great event coming up in Victoria. So we're coming over from Metro Vancouver. That's very exciting. And then our next Decarb Lunch is on heat pumps gone wrong and how to fix them. So a spicy topic that I know a lot of folks want to listen in on and figure out like what solutions have been pitched and are making our buildings better. So with that, I just want to thank Alex and Franz and Elise and Simon again so much for your time, and thank you to the audience for making these events what they are. Thank you so much.
Thank you.
Thanks.
Thank you.
Have a great rest of your day.